inside it is a crossed mark will be there, that is the tensor. So it is a way to combine vector space, and it is qubits behavior is entirely described by using tensor, right. So I think in the previous lectures you have seen a representation 2 to the power n, right, you've seen. So what is a 2 to the power n? 2
multiples of n.
2 multiples of n. So what is that n? Suppose 2 to the power n is 1. 2 to the power 1 is 2. Yeah, I agree, super. What is that 1? And if it is 2 to the power 2 is 2. What is that 2?
Power.
No. No. State of, right. Suppose you are having your quantum computer. You are having 16 qubits. How to represent that 16 qubit? 2 power 16. No. If you do what? You will get 16. 2 to the power 4. Then what is that 4? Now tell me what is that 4? Your number of qubits. Your number of qubits. So if your qubit increases, your computation is increases. Super. But what is there inside a first single qubit? So 1 qubit, fine, everything is fine, there will be 1, 1, 1. Now we are having 2 qubit. So what happens? 2 to the power 2. So how many things? 4. 4 entries will be there. How to handle that? Values you will handle. You are having calculator, you will work it out. But it is not like that. It is an entity, quantum information. So how it is? The computation is how carried out. So for that we need tensor product. See, look at here. The problem comes how to deal more than 1 qubit. So where the problem arises, suppose we are started using more than 1 qubit, there we are what? Finding difficulties to, no, there is algorithm, there is process, but being a computational guy, we should know how internally it works. How internally, see, each qubit have 1 Hilbert space. So what they are saying, each qubit is having 1 Hilbert. Suppose there is 2 qubits, there is 2 Hilbert space. So continued in one note. Now let us go to அப்படி பண்ணாலுமே வர மாட்டேங்குது. It is not coming. No, it won't come. So there is problem in the projection of the projector. Okay, please fix it and let me come back to this. Yeah, fix it please. No, look at here. This is a simple most zoom. It won't work. It is not the problem from here. It is a problem in the projector's projection. We need to fix from here. Yes. Okay, so let them fix. We will go here, right? So already you know matrix multiplication, right? How matrix are getting multiplied? Suppose we are having A and B are 2 matrix. How it is getting multiplied? Dot product. So it is dot product. What is cross product? So okay, so instead cross product, they are having inner product. They are having, so in the earlier operators we have seen, in the second operator we are having Hermitian operator we have seen. Hermitian, there are 2 properties. One among them is going to be inner product. One is going to be inner. So the process to do is we need to convert into column vector as well as row vector. Suppose we are having x and y coordinates, the x will be converted into row vector and y will be converted into column vector. How to work with row and column vector? So we need to take inner product between them. Step 1, C1, C2 and C3, look at that, it is called ket notation. Column vector is represented by ket notation. The second is what? The second step is we need to convert row vector. Row or column?
Row vectors.
Super. So that is R1, R2 and R3. We need to take the product of C1 bar R1. So ket notation as well as bra notation. So that is X or Y. Inner product will be ket X over, bra X over ket Y. Right. X1, X2, X3 is your column vector. Y1, Y2 and Y3 is your column vector and row vector. Row as well as column. Right. Suppose we are having 1, 2, 3, 4 is the value we are having. Now we need to convert 1, 2, 3, 4 into column vector into and row vector. So 1, 2 is R1, 3, 4 is R2. Correspondingly we are having B. So Cn 1, 2, 3, 4, 5, 6. Now we need to convert this 1, 2, 3, 4, 5, 6 into column vectors C1, C2 and C3. 1, 4, 2, 5 and 3, 6. Now we need to take A dot B. See R1 bar C1, R1 bar C2, R1 bar C3. In the bottom we have R2 C2, R2 C3 and R2 C1, C2 and C3. There is a naming error. 1, 2, 3. Replace C1, C2 and C3. Right. Now come to the actual values. 1 plus 8, 2 plus 10, 3 plus 12, 3 plus 16, 6 plus 20 and 9 plus 24 and the final product 9, 12, 15, 19, 26, 33. This is the inner product of two vectors. Inner product of two vectors. So step 1, it should be converted into then step 2 is what? It should be converted into column vector as well as row vector. This is the fundamental process happening in your qubit, single qubit. Suppose we are having single qubit, this is the process. Till we are not seeing the symbol circle with into mark. Whenever the circle into marks comes into picture, then we are going to be what? Going to deal more than one qubit. More than one qubit. Right. Now we are having what? Tensor product of two matrices. Now we are having two matrices A and B. Their elements are going to be A11, A12, A21, A22, and we are having B, B11, B12, B21 and B22. Now we need to take tensor between these two. So now we can keep it as A will be qubit 1 and B will be qubit 2. So this is what happening. Suppose we are having two qubits, right? What is the outcome? Look at the number of elements. Now look at the number of elements. It is not like the case earlier. 4 entries are there, but now look at here. It is this is what exponential. If the number of qubits increases, what increases? Hilbert space increases, then the information is also getting increased. Suppose we are having 156 qubit in our quantum computer. Our normal desktop will not able to handle the information which is available in the 156 qubit. That ratio and the details, it is there in the later slides, will show you how many states and how many classical bits required to represent the quantum bit. We'll see. Now look at here. This is product of A tensor B. Product of A tensor B. See, please work it out as it is. It took a lot. You are writing in pen. I used to write this in digital pen. So it will come later, but practice. Note it down as it is. A11 versus your B11. A11 versus your B11. Then A21 with your B11. On the right hand side, what is there? On the right, we are having A12, A22. So this is A tensor B. Right. Leave it. So now tensor product of two vectors. Noted. Okay, note it down. This is tensor product between matrices. We are discussing tensor product between matrices. So this is very simple. A tensor B. These are all the entries 1, 2, 3, 4. Right. Now we need to process tensor product of vector. So any guess what is a tensor product of vector? What might be the output? If you take tensor product for vectors, what will be the output? It will be a vector or what? Definitely it will be a vector. Definitely it will be a vector, no doubt. Right. So it is otherwise called Kronecker product. It is otherwise called Kronecker product. There is a slight difference. In the earlier step, what we are doing, we converted row vector and column vector. But now look at there. There is no what? There is no bra entry is not there. It is there only what? Ket representation is only there. That is the beauty of what? Vectors. Tensor product between vectors is having only what? Right. So x will be x1, x2 till xn, and y will be y1, y2 till yn. So then obviously it is x1 dot y1, x1 dot y1, x1 dot y2, x2 dot y1, and so x2 dot y2, xn dot y1, it is xh, not n, xh. The representation is xh, not n. Right. So that is the expression. Now we are having two example vectors. So what is the symbol? Psi is state of a quantum system. Psi is what? State of our quantum system. Then the corresponding two states. AB is one state, CD is one state. What is the product? As per x1, y1. So what is the product? You try. It is very simple. Just work it out. So it is AC, AD, BC, BD. Super. Now we are replacing that entity with scalar value. Now we are replacing the vector with the scalar value 2, 0, tensor 3, 1. So in this way what works? Qubit works in this fashion only. 2 to the power 1, 2 to the power 2, 2 to the power 3, then what happens? The rows and dimensions are getting changed and the number of output is also what? Is getting exponential. So only classical computer struggles to work it out these kind of things. Right. So till that completed. 2, 0, tensor 3, 1 is what? 6 to 0, 0 is the output of that 2. Right. Now, so why you may ask, why I am discussing all those steps? Now look at there. We are trying to take, I think you are expert, you have attended 3-4 lectures from yesterday, day before yesterday, right? Look at there. So what is this? These are all possible states of what? 2 qubit quantum states. So suppose there is 2 qubits, how many states will be there? 4 states starting from 0, 0, 0, 1, 1, 0, 1, 1. So try to get the tensor product of state 0, 0 and 0, 1. This is what happening in 2 qubit. You have seen these numbers. I think you might have seen these numbers somewhere in the textbook or in your research paper, right? What is the process behind this? The process is what? Kronecker product or what? Kronecker or what? Product of vectors. Product of vectors. There we use only ket notation. There we use only ket notation. There we use only ket. Super. 1 0 0. If you take tensor product for 0 0 state, it will be 1 0 0. Next. 1 0. 0 1 0 0. Right. So you can try 1 1. You can try tensor product of quantum states 1 1. 0 0 1 0 0 1. I think I am not sure. Work it out and tell me. I am simply saying. And try 1 0 1 0 0 1 we have already. Try 1 0. What is 1 0? 0 0 1 0 is what? 1 0. Right. So what is it? Product of quantum states 1 1 0 0 1. Is it right? 0 0 1. Right. And now you tell me, where are you now in quantum computer? This is quantum states 2 qubit. Now you are working with 2 qubit. So this is what happening in a 2 qubit quantum computer. Definition 0 and 1. Now we are processing 2 qubit. We processed a single qubit. Now we are processing 2 qubit. So 2 qubit computation process. Right. Right. We need to go down. Next to this. Now only we are coming to the definition. Mathematical definition of. So there we have classical computing. Now look at the right hand side. Quantum computing definition and one example quantum operation. Right. So what they are concluding on the left hand side? Classical operations are not reversible. Classical operations are not reversible. On the right bottom, you take a look what they are saying. Operations are reversible because of unitary operator. That is the beauty of unitary operator. Unitary operator only does this. It reverses the process for your quantum computer. Look at there. We are applying Pauli X. We are applying Pauli X and 0. So what is the entity we are having there? What is the first one? That is Pauli matrix. There is two matrices. The first matrix is Pauli. Second matrix is what? State representation of 0. State representation of your 0. What is the output? If you apply Pauli X, what will happen? If it is 0, flipped automatically to, not automatically, flipped to 1. If we apply Pauli X to state 0, what is the output? 1. It is 1. Right. So, in the next, we are applying Pauli X to state 1. First matrix is what? The Pauli matrix. What is the representation of 1? 0, 1 is the representation of your state 1. And look at the output. Work it out. You will end up with 0. Single qubit operation. Pauli X is what? Single qubit operation. Pauli X, Pauli Y and Pauli Z. Pauli Z is not like that. Pauli X, Z is third projection operation will be there. I will comes into picture. There you have negative value. Pauli X and Y is similar, but Pauli Z is not the same. Pauli evolves around Z axis. Pauli X revolves around your X. Pauli Y revolves around your Y axis. Right. Right. Then we will go a little bit up. Now you read this. This is all your classical computer and your quantum computer, your 2 to the power n. Now tell me what is the 2. Now you are clarified with n. Now tell me what is the 2. N is number of qubits. Now tell me what is the 2. So qubit is 1, that is n. Then what is the 2? Your base states are what? Superposition contains how many states? 2. That is your 2. 2 power exponential. So qubit increases, your information is also increases. So they are saying, suppose 258 qubit or 256, I am not sure. It is not enough to what? Store in the entire universe. Universe is not enough. Suppose we are having 256 qubits. How many classical bit is required? The entire universal classical bit is required to decode the information available inside the quantum computer capable of having 256 qubits. 256 qubits. Why? Because of this 2 to the power n. 2 to the power n. Keyboard வேலை செய்யாது இருங்க. Yeah, let me do it. என்னோட பொருளை என்னால் தான் மேனேஜ் பண்ண முடியும். இது ஒரு வித்தியாசமான லேப்டாப், அதனால தான். Right. Now look at the statement. Yes, please let me know if you have any doubts. Now you are very strong in what? The quantum computing and its basics and its the maths behind it. And its maths behind. So what is left out? So single qubit we have seen. We need to see how multiple qubit works. We have seen the basics. How multiple qubit works? It's simply tensor product. But if it comes to gate, the operation is slightly different. If it comes to gate, the operation is slightly different. Any doubts so far? It's a tensor product. What is happening in quantum computer? It is simply what? tensor calculator. Quantum computer is a linear algebra calculator or tensor calculator, we can say. Tensor calculator. See, linear in size input, exponential in size input, state space is n, states is going to be 2 to the power n. And the notation psi alpha state 0 plus beta state 1. Alpha and beta is what? Elements in a complex Hilbert space. So at the end, what is it? It is a scalar number. We are getting output as scalar number. So almost we reach the end of quantum mathematics. Now look at this representation of qubits. If it is decimal, that. If it is binary, representation of qubits using decimal, representation of qubits using binary. 0, 000, 1, 001, 2, 010, then 3. So later this will reflects in quantum register. This will be reflected in quantum register. This is the principle used in quantum register. Right. Any doubts so far? So quantum computing definitions, basics, principles and their operators and how it works. So we have completed till single qubit. Now we will continue from multiple qubit. See, hereafter we don't want this gentleman, we will leave him. Right. So now we will see what is there in the quantum computer. Right. So that definition we have seen in the one note earlier. Representation of qubits. See, look at here. Controllable unitary evaluation. The important principle of quantum computer is what? Controllable unitary evaluation. So what does it mean? Total probability is equal to 1. So that is the controllable unitary. So that is the reason we are able to reverse the process. And the preparation of qubits for initial state. So this is the first step. If you have any quantum computer, what is the first step? Preparation of initial qubits state get 0. Then what is the last step? Measurement of your qubit with respect to collapsed either state 0 or 1. So this is a typical image of superconducting. It is a quantum computer of type superconducting. So this setup is cryogenic setup. This is called what? Cryogenic. So in that environment, sustainable to maintain 1 Kelvin to 567. 1 Kelvin is almost minus 273 degree Celsius. So when it emits the particle, ground state will be ground will be shifted to excited at minus 273 degree Celsius inside a protected chamber, or what it is called the dilution fridge, right. Quantum computer parts, what are all the parts available inside a quantum computer? QPU, it looks like a shiny metallic surface. It constitutes all the qubits. So then the tiny lines are, then there is a lines and loops are microwave resonators. So generally which phenomenon they are using? Superconducting principle. So when superconducting behavior happens in special materials like vanadium, graphene, etc. So my question is, when superconducting means almost resistivity is zero, they are saying that material is what? Whatever it is there, it conducts everything from one side to another. When 1 Kelvin ranges from 1 Kelvin, there is tilt symbol, there is tilt, right. Next is what? Dilution refrigerator. So this component is responsible for protected temperature. So job is to cool the quantum processor. You know which is the coldest place in the universe? Iceland. No, there is a city in Russia, I forget the name, it is some name. Right. No, it's not that. There is a quantum computing lab available in US called Nebula. The coldest is no longer than boomerang, it is now the quantum chip inside this fridge. So it is looks like a large cylindrical, it is 4 feet height. The dimension of the dilution chamber is 4 feet tall. 4 feet tall. So there is inside multiple shields of layer. So if layer goes up, what happens? Layer goes up, the temperature decreases. Exactly, this is what your dilution refrigerator. Next part is control electronics. There is an interface between classical and quantum. It is called control electronics. So microwaves are used to do such thing. So they send microwaves to the quantum processor and performs the calculation. So converts the quantum algorithm into quantum instruction for qubits. It is connected with dilution chamber. Control unit is connected to dilution chamber, then the remaining part is classical. The next one is, we are classical computing expert, right? So microwave, which generates signal conditioning, processing and amplifying signals to measure and control, data processing. So I told you earlier, so what is the equivalence for a qubit? So this we did earlier. Tensor also we are aware. single qubit gates. Right. Now the Hadamard. Right. So what is the output of Hadamard? Output of Hadamard. In morning we have seen plus and minus. Plus and state plus and state minus is the output of Hadamard. Hadamard is also what gate? Single qubit gate. Hadamard is also single qubit gate. So where we are using quantum register is what? Tensor products are used to do what? Quantum multiple qubits formed to function like a quantum register. So number of computation doubles, the number of qubit increases. Right. Example, one example for tensor product. Right. Hadamard gate working. So this is a workout for how we are getting plus and how we are getting minus. Right. Now we need to see what? Multi-qubit systems. So C0 gate is the gate which implies what? Multi-qubit system. So in this we are having two qubits. One is for control purpose, the other one is called as target. The one is called control, the other one is called target. So when control is going to be 1, it automatically flips the targets, flips the target. So we will look into the truth table. So here Q1 is what? Q1 is control and Q2 is target. C0 gate, it is exactly XOR in classical. So if first control qubits 1, then what happens? Second target bit is flip. So draw the table and try to work it out. Truth table for C0, else remain unchanged. Right. It's the truth table of your C0 with respect to control and target. With respect to, so where you are able to see the change at the bottom when the what? The control is going to be 1. So look at the target is going to be 0, flip to 1. When control is going to be 1, if it is 1, the target is flipped to 0. Right. You may ask why? What is the beauty of C0? No, what is the beauty? Okay, what are all the basic blocks of quantum computer? Superposition, entanglement. How we are achieving entanglement technically? Theoretically entanglement is fine. What is the theoretical example for entanglement? Theoretical examples for entanglement. Whatever it is there in the first qubit, it will be implies or what? The next qubit, right? That is what your entanglement. Say one example for entanglement. If a person is copying from his neighbor, if the first person is written wrong, the copying person content is also what? Is impacted with respect to the original content, right? I think see listen, when we are attending a lecture from IIT Kanpur, my instructor gave me an example from Telugu industry movie Nagarjuna, which is acted. There is double act Nagarjuna is there. One is innocent guy who is in the prison. Yes, right. It's an example for your entanglement. Example for whatever he does, what happens? it impacts the second one in the present. Example for your entanglement. Super. But how to achieve in quantum? Hadamard plus C naught provides what? Entanglement. Why we need entanglement? That is my next question. Why we need entanglement? No, that is my question is yes. If something is like that, what is the benefit?
At the same time.
There is a small clue resides here. If you want to develop any algorithm, in quantum, we should think which part we are putting into entanglement. There we are able to get what? The advantage. Suppose we are having classical optimization. Suppose you are developing quantum optimization algorithm, which part of classical lags that we are putting into the entanglement, it produce what? It produce the difference. Quantum optimization. So what does it mean? Which part we are projecting into entanglement? It matters. Most of the quantum algorithms is what? Speaks about what? Which part is put into entanglement. Which part is what? Put it into entanglement. That is the beauty. So what is important? C naught is important. Hadamard and C naught is important. Right? C naught 0 0. What is internally happening? Look at that. That is a matrix under the 0 0. Look at the final output. Look at the final output. Super. Look at here. Look at here. What is there in the left hand side? Qubits. In order to represent one qubit, how many bits required? 512 bits required. In order to decode information one qubit, how many classical bits required? 512 bits required. Basis states how many? 2. By default it is 2, 2 to the power n. So that's what it is, 2. Then 2 qubit. So 1024 bits required to decode information from your 2 qubit states. Basis states 4. Look at here. 1 by 2 state 0 0 plus 1 by 2 state 0 0 0 1 1 0 1 1. Right, then 3 qubits 16 kilobytes, basis states 8. Then there is what? 1 by 2 state 0 0 0 plus 1 by 2 state 0 0 1 and so on till 0 triple 1 till 0 triple 1. Right. So morning we were speaking, right? Types of qubits are there, right? Superconducting is one type of qubit. What happens? There is zero resistivity, then cavity, QED, photonics. I think you people might hear Xanadu. There is a quantum player available in Canada. They are named as what? Xanadu. It is a photonics based quantum computer. Then trapped ions is another type of qubit. Then neutral atoms. Then neutral atoms is one type of quantum bit. Nuclear spins. Nuclear spin, otherwise NMR, nuclear magnetic resonance. Yeah, now you read this, you will get a better picture. So in this, find out which quantum computer is almost room temperature. Which quantum computer we can maintain almost in room temperature. Take a look. Mostly the 2 is what? Cryogenic setup is required. Which is not requires the cryogenic setup? Look and tell me which one. Particles of light you are able to see. For that, what is not required? Cryogenic setup is not required. First 2 is what? It requires cryogenic setup. Dilution chamber is required. Superconducting and trapped aluminum or niobium at absolute 0 minus 2 degrees Celsius. So who are all the players? IBM, Google and Rigetti. They are using superconducting qubits. Next. What are the brands? Trapped. Honeywell. I think you heard Honeywell. Honeywell is one big player in quantum computing. Then ionic photonics. Xanadu and psi quantum. Xanadu and psi quantum. Neutral atom. Look at the player. Dirac. Helium and nitrogen are called what? Neutral atoms. There is a cavity between your neutral atom. There what happens? There computation takes place. There computation takes place. Right. Look at here. The power of quantum computer lies on the 2 cornerstones, interference and entanglement. In which part we are putting into entanglement, which we are minimizing from your interference, minimizing errors through interference, which part we are putting into entanglement. That is the edge of quantum computer. Interference says what? Interference says what? I think you can read. So this is the main thing. Enhance what? Correct solution. Classical computer, the problem is what? It cannot enhances. Whatever it is there, it provides, it produces and send it out. But what is the beauty? It tried to rectify error correction. In quantum computing, there is a hidden area called error. Only quantum experts who is having more than 10 years, they have a prompt knowledge in error correction. The dummy quantum experts will never open their mouth regarding what? Only who is having that actual knowledge, they speak about error correction. Is a very prompt area in quantum computing. NISQ, that is noise intermediate scale system, that is NISQ. Right. Entanglement means what? Entangle means combined state of what? Qubit contains more information. So you suppose we are doing computation, which level is considered as pure quantum? If you use more than 100 qubit, those problems and those applications are what? Purely quantum computing. So we should use more than 100, not possible. So we need to subscribe packages from IBM like IIT Madras, IAC, they are having subscription. They are running their research work in real-time hardware through IBM. So that is purely what? Quantum computing application. Right. Super. So what are all the softwares available? Qiskit. What is Qiskit? What is the expansion for Qiskit? Quantum information toolkit is what the Qiskit. Super. Then Xanadu, Penny Lane. Suppose you are working in machine learning, you can go behind which one? Penny Lane documentation. The coding is simple. The main problem with the Qiskit, recently they are what? They are frequently changing the version. So what is not possible? Using the same code. Suppose you are doing a project, Before 1 month you had a code for QML, that code will not run from today. So that is a huge headache in Qiskit machine learning packages. So I suggest you go behind what? Pennylen for QML. See, inside Pennylen also what is there? They are having Qiskit packages only, but it is simple to use. Google Circ. Then who is the other one? Microsoft. What is the tool they are having? Q Sharp. These are all the various softwares for, right. I think you people are very much interested to know about this only, previous. Yeah. So what is time now? IBM Qiskit, Xanadu Pennylen, Google Circ, Microsoft Q Sharp. Right. Software for quantum computing. 3:30. So what is your assumptions regarding quantum applications? So may I know your department? So computer science. Oh, majority are from computer science. Okay. What about others? ECE? ECE. Okay. Physics is there. Okay, super. Chemistry. Quantum chemistry is a major revenue generation for what? Quantum application. If 100 rupees is generated from quantum computing, 60 belongs to quantum chemistry. 60 belongs to quantum. Example, Nordisk. You know Nordisk is a medical drug. He is Italian based MNC who is dealing with what? IBM works with Nordisk. IBM works with Nordisk. They are doing something with insulin. I am not sure what they are doing. One is what? Quantum chemistry is a major revenue generation. Molecular prediction. Molecular prediction. I think it is called molecular dynamics. See, whenever we used to attend some meeting in IAC, there are some professor, they comes from biotech and they talks about this molecular dynamics. We don't know what is at all. Basically computer science, right? Yes, yes.
Qubits can be controlled and measured
Reliably? No, not at all possible, because listen, so there is a professor called Apurva Patel. He is called Indian Feynman. He is from Indian Institute of Science. Apurva Patel. He is called Indian Feynman. His one-line statement: quantum computing is highly fragile. The point is what? When qubit is coherent, when it is going to be decoherent, we may not know. So he claims it is highly fragile. We cannot able to control what? We cannot able to control the coherence. Still the coherence time is seconds. 43 seconds, 50 seconds, 60 seconds. Qubit works productively how long? 40 to 50, 60 seconds. That is the problem with what? The quantum computers. It is highly fragile. It is not possible to do say what? Deterministically it will work like that. No. It will go down any time. So rerun the programming is not possible. It is measured and it is getting collapsed. It is what? Starting from the scratch, go step by step, finally measured. From there running is not possible. Wherever we live, from there resuming is not possible. It is started from the scratch. Start from scratch. Right, softwares. Right, we started about applications. Yes. What is your guess? Chandrayaan. See, Rolls, you know Rolls-Royce. Rolls-Royce is also working with IBM. Rolls-Royce, Daimler. You know Daimler. Who is Daimler? The parent company of Mercedes-Benz is called Daimler. They are also working with IBM. Then Tesla, I am not sure, I don't know. See, most of the engineering domains, they are working with quantum computer. Mechanical, aerospace, logistics, and chemistry, and we will see elaborately in the upcoming slides. Mostly all applications are covered. Airlines, JP Morgan, you know IBM, most of the resources of IBM is free. Why? The gentleman JP Morgan donates that much huge amount of money to IBM. So what? The most of the resources are free. Who is behind it? JP Morgan Chase. He wanted to predict. JP Morgan what he wants. He want to predict the stock market, and he want to what? Suck everything from what? Upcoming stocks. So what he is trying to do? He want to build portfolio management. Which portfolios are growing? So he want to predict by using quantum computer. He wanted to generate revenue by minimizing that risks. So he is focusing on what? Banking and financial. Chemicals. Any guess? Chemistry department, any guess? Super reaction, for which mostly expected for what? That we will, when you think we will see. Chemicals, electronics. In electronics, in which part? See, I have registered for IISc 3 successful years, but last year I have not turned. For the past 3 years, whenever we go for quantum computing workshop, they teach chip design. What they teach? From Keysight Technologies, they provide licensed version for a week. They teach what? They teach chip design. Why? Quantum is also a processor. For that also what is required? Chip designing is required. So they are what? Keysight sponsoring IAC like anything. For that QRP, Quantum Research Park is there. For their event, the major sponsor is whom? Keysight Technologies. Government. Government is funny. Why? Tell me. There is a super thing is going on between ourselves and our rivalry. You know China what is doing? Record now, decode later. He steals every country's data. China steals, not only India. Most of the government data they are stealing. Whenever their quantum computer is going to dominate, then they will decode the information. Record now, decode later. That is a China's practice in what? Stealing information. Once their quantum computer becomes superficial, they will decode what? Most of the cultural data, not only India, most of the countries. So government should have what? Post quantum. There is a thing called what? Post quantum. Post quantum cryptography. There is a domain called what? Post quantum cryptography. We should have a resilience or reliable security mechanism to what? It cannot be predicted by what? Quantum computer. Healthcare. Health. One example I told Nordisk. Insurance. Life sciences. Logistics. See logistics. How many of them aware of logistics? Revenue generated by logistics. It is very huge. When we started in 2020, we started learning quantum computer by 2020. From 2020 till now, there is a classical problem, optimization, route optimization, and logistic route optimization is a most wanted domain in quantum computing. Billions of what? Income is generated in quantum optimization. So when shall we stop? We'll stop and say, I know you are very curious about QML. So there is one thing that we will I will show what is a thing to be done for QML and a sample code. Let us stop. I don't want to dose you with all the PPTs. I have all the PPTs. It doesn't mean that if I have PPT I should deliver to you. No. I have some sequence and logic. In the logic I used to deliver, you need to able to decode, you need to what? You need to go through in which direction we can proceed further. Almost we reached. There is a reason why I am exploring this. So when shall we have a break? If you don't want a break, we will continue. Choice is yours. If you people are interested, you can take a break and we will continue. See, please refresh yourself and come back. No issues. See, we are all human beings. Nature calls. What do you mean by nature calls? Every 2 hours, what happens? Every 2 hours, what happens? If we give liquid input to our body, the process completes every 2 hours. No, that is fine. No, nature calls. Nobody restrict nature calls, right? So please take your time. We will continue with the example applications. We straight away jump into QML, then we will see sample code. We will stop there. Now you should be able to understand. There are many things, but it is not that you should what? You should grasp everything. Whichever is feasible in this time slot, we will put that only. Please take your time. Yeah, okay.